And without further ado, I am delighted to introduce our next speaker, Dr. Loaiza, who is a battery researcher and is a passionate battery scientist. She was first introduced to the field through the Master Erasmus Mundus program materials for energy storage and conversion. Following, Laura obtained her PhD from the Université de Picardie, Jules, Verne in France 2019. In 2019, is currently working as a postdoctoral researcher at the Chalmers University of Technology in Sweden. Her major interest is the study of processes taking place inside the battery during charge and discharge, and new battery technologies that are more cost-effective and environmentally friendly. So, without further ado, Laura, please go ahead.
Thank you really much, Adam, for the very nice introduction. And thank you to the organizers for inviting me to this Congress. So, as you said, today I'm going to speak about energy storage, particularly about batteries. So, I come from Colombia, from a very small town called Salento, and over there I have done my bachelor in chemistry. Following, I came to Europe to join the Master Erasmus Mundus program for energy storage and conversion. I did my PhD in France on battery materials, and currently I'm working as a postdoc researcher in Chalmers University of Technology in Sweden. So in overall, I would say my background is material science applied to batteries. So as we know, we nowadays live in a very energy-poor society. Our needs for energy is constantly increasing, and with it as well the greenhouse gas emissions. So unless we leave this dependence from fossil fuels, this tendency will continue. And batteries will play a very important role in enabling us this energy transition, because they will enable the usage, more efficient usage of renewable energies, and they also play a key role in the electrification of all the transport media. And also we see that batteries are everywhere, in your phones, in your laptops, and in many other devices. But batteries are not something new. In fact, they were discovered more than 200 years ago, when Alessandro Volta assembled one of the very first electrochemical cells. And over the years, we have seen many other different types of devices and chemistry that have emerged. And it was only until 1992, with the first commercialization of the lithium-ion batteries by Sony, where lithium became one of the dominant technologies. So despite the fact that we have many different types of batteries, they all have the same principle of working. So we have a negative electrode and a positive electrode separated by an electrolyte. And if we now take the example of a lithium-ion battery, that is the battery that most of you have in your phones. So the negative electrode, the anode, is composed of graphite, and the positive electrode, the cathode, is composed of a lithium metal oxide. And the particularity of these two compounds is that they have a layered structure in which lithium can move freely in between the layers. So when you plug your phone to charge your batteries, the lithium ions will move from the cathode to the anode, and then when you use your battery, they will move from the anode to the cathode. And it's this movement back and forward from the lithium ions that allows you to have energy from your battery. And indeed, the particularity of these two materials to host lithium in such a way, and the fact that they are compatible in between them, was awarded by the Chemistry Nobel Prize in 2019 to the creators of the lithium-ion batteries. And so you might wonder why lithium is so important, why is the dominant technology? And the answer is that size matters a lot. You don't want to have a very big battery with your phone, or we don't want the battery in the cars to be occupying a lot of space. So ideally, we want to pack as much energy as possible in the smallest space possible, something that we call energy density. And if we have a look at the periodic table, so we find that lithium is the lightest metal, And also in its ionic form, it's a very small ion. So if we want to store a lot of energy in a very small space with a lightweight, lithium is a very good option. And that is why it has been the dominant technology for electric vehicles, computers, and phones. But in reality as well, is that a battery is very complicated. When I show you the schematic of how a battery works, it was very oversimplified. The truth is that there are many processes happening at the same time when you charge and discharge your battery. Some of them, we don't want them to happen, like materials degradation, corrosion processes, or the formation of unstable interfaces. So what we do in the lab as battery researchers is to use different type of model cells in the lab scale to mimic the conditions in which a battery is charged and discharged in daylight, so that we can identify all of these processes happening, understand them, and correct them so that we can use our batteries in a more efficient way. Because in the end, what we want is to have a high energy density so that you can use your phone for longer time or drive the car for longer distances without charging the battery so often. We also want a long cycle life so that the battery can last for many years. We want it to be low cost. We want it to be easy to upscale, meaning that all the discoveries that we do in the lab scale can pass rapidly to an industrial level so that we can answer to the increased demand and to the call for the energy transition. We want it also to be safe. Many of you are familiar with or have seen pictures of battery exploding, and this is mainly to the presence of a liquid electrolyte that is composed of flammable solvents. And by replacing this electrolyte by a solid one, we can increase the safety of the battery and at the same time prepare batteries that are smaller and even flexible. We also want the batteries to be sustainable. If we have a look at the natural abundance of the elements in the periodic table, we see that lithium and cobalt and nickel, which are other components used in batteries, we have a limited sources. And so ideally, we want our battery to be made of abundant elements. And because the demand is constantly increasing and we expect it to increase even more and more, so we need also some recycling approaches and moving towards a more circular economy where the batteries can have a second life after they finish to be useful for a certain application, and when we can recover all the elements in the battery and to prepare new ones so that we can use more efficiently all the resources we have available. So if sustainability is one of the key factors in batteries, so can we prepare batteries from other materials besides lithium? And so if we have a look at the periodic table again, so we know that elements that are close to each other behave more or less in the similar way. And we know that close to lithium, there are many other elements that are more abundant. And indeed, we can prepare batteries from sodium, magnesium, aluminum, potassium, and calcium. The sodium-ion technology is already in the prototyping stage by two different startups, Tiamat in France and Faradium in UK. And we see the other ones also a lot of research going on how to perform this as a batteries. But we see that the weight for these elements compared to lithium is higher. So if we want to pack more energy in a small space with lightweight, then we will have problems and lithium will still be the dominant technology. So making our battery from more abundant materials often comes at the cost of having slightly lower energy densities. But there are many other applications for which the size doesn't matter, because in this case, we will have to make batteries that are heavier or bigger. And for the stationary storage, we can make batteries as big as a truck or even bigger. And this freedom to make batteries in different shapes have also boosted the research in other different type of technologies. For instance, the redox flow batteries, in which the positive and negative electrodes are liquid and they are contained in very big tanks, and it's already commercialized. We have the liquid metal battery that works at high temperature so that all the elements in the battery are liquid and already in the prototyping stage. And we even have batteries that can use seawater to store energy also in the prototyping stage. So we have a lot of different ideas and a lot of different technologies that aim to prepare batteries from more abundant materials with more environmentally friendly and at a lower cost. Because we will need a lot of different type of technologies because the applications are very broad. For instance, if we take the example of the renewable energies, so batteries will enable a more efficient use of these technologies by storing the excess of energy and then releasing it when it's not needed. When it's needed, for instance, in the night when the solar panels are not working or when there is no wind in the case of the winds. But also because our energy consumption of energy fluctuates during the day, there are certain hours in the day where we consume more energy, and linking the batteries to the energy grid will allow to supply this excess of energy that is needed and allow to use more efficient use of the energy that is produced and to reduce the losses. So finally, I would like to leave you with a picture of the different type of the different factories, gigafactories that are being built in Europe in the next years. So we see that batteries are really helping to the energy transition by enabling a more efficient use of the renewable energies, and also they play a very important role in the electrification of all the transport sector. But we still have many challenges to overcome. For instance, we need to make them more sustainable, more environmentally friendly, and lower the cost of productions. And we also need to understand all the processes that are taken inside the place of the battery in order to access its true potential. And it's here where research plays a very important role. And in the end, we will have many different types of other technologies because the applications are very broad. So there will be one technology for each application, and we will be able to answer to this energy transition by combining all of them. So you see, there is a new chapter open for battery research, and I hope that you, the young people, will take part on it. And with this, I finish, and I will be more than happy to answer any of your questions. Thank you very much.
Thank you so much, Laura, for that talk. And on a topic which is highly relevant to everyone's daily routine and daily life, we're absolutely dependent on batteries in many different forms and things. I think we have enough time for maybe one question before the next speaker. So someone has asked, can you explain how a circular economy can exist for batteries?
Yes, so there are many projects at the European level right now where they plan to build the fabric of the battery and the place for recycling it just directly in the same space, so that we can use the battery, and then for instance, if a battery is used for a car, sometimes it can have a second life as for other applications that do not demand so much energy. So this is one of the aspects to get to a circular economy. The other one will be the recycling strategies, which is a little bit more complicated because the main problem is that every manufacturer of battery has his own cost, his own formula to make the battery. So meaning that for recycling them, we need to have a process that can process all of the batteries regardless of their composition. And this is where it becomes very complicated. So ideally, we want to standardize all the way in which the batteries are produced, so that they will be easier to recycle, and then from there use these recycled materials to prepare to fabricate new batteries.
All right, thank you so much, Laura, for answering that question. There's another question in the Q&A function, but we don't have enough time to go through it now. So if you don't mind, perhaps replying to that in the chat, that would be great.
Yes, sure. Absolutely.
Thank you so much again, Laura. Please do show your appreciation for Laura's amazing talk in the chat. Perhaps write down what your take-home message you got from the talk was as well.
Thank you very much.
Thanks, Laura.